morning, I guess. I'm excited. It's Hanukkah morning. What I'd like to talk about today is commonality variability analysis and how we could use commonality variability analysis to perhaps reduce some complexity when talking about the domain. I'm Avraham Poupko. I've been, for the last couple of decades, an architect in the pay TV industry. I currently work for a company called Cinemedia. It's based in Jerusalem, Israel. And the topic that really fascinates me, that I like talking about and learning about and reading about, is how people join to create that amazing thing called software. That's what I like to learn. A couple years ago, I spoke here at the Domain-Driven Design Conference, and I spoke a bit about complexity. I spoke about the importance of multiple models. And I showed the following slide. And I said that the complexity of the solution will always be greater than the complexity of the domain. The complexity of the solution is always going to have something beyond the complexity of the domain. When I say domain, I mean the part of the domain that we are addressing the needs of. We know how to make complex solutions for simple domains. We don't yet know how to make simple solutions for complex domains. And when we talk about tackling complexity in the heart of software has a heart, and in the heart of software is complexity, we're talking about that extra complexity, what we might call accidental complexity, where you have a domain, which might be simple or complex, and then you have a solution, and you hope that the solution is not more complex than the domain. And that's what I spoke about. And I said that one of the ways to reduce the complexity of the solution to the complexity of the domain is by having multiple models. Multiple models allows you multiple perspectives. So that's what I said then. And today I would like to dive into that a little more. Now, every time we create software, every time we write a routine or a function or a program or a module, we're operating under several beliefs. We believe that the world is similar enough that it is worth automating. Very, very few programs are ran only once. Most programs that we write, most functions that we write, most routines, most operating systems, most compilers will be run more than once. And when we run them more than once, we think that those executions are similar enough that it's worth automating. We believe in automation. We have another belief. We believe that the world as it is at the time that we're designing the software and the world as it will be at the time that we execute the software will be similar enough that it is worth writing software. If we didn't believe that, then there would be no point in anything that we do. So those are some of our beliefs. On the other hand, every time we put in a parameter or a variable or a switch or a control of any kind or a runtime variable, compile time variable, we're saying things aren't exactly the same. We have to parameterize them. So I wrote the function because I believe that things are the same, so I want to write a function. Then I write a parameter because I believe that they're not exactly the same. Or I write some sort of configuration switch because I believe that the world as it will be is similar enough to the world that it is now, that it is worth designing, implementing, writing, and delivering software, but I don't know exactly how that world will be, so I allow myself some flexibility by putting in some controls, some variables. And one of the cost drivers, I might even say the cost driver of software, is getting that right. If we make a software too rigid, it becomes unusable. And if we make a software too flexible, it becomes unmanageable, and it's very, very hard to do it. And finding that fine-tuned balance between how much do I automate and repeat, and how much do I parameterize, and how much do I make into variables is perhaps the challenge of software design. And a lot of good stuff has been written about it, and as software developers, those of us that are software developers, either in the present or in the past, We get that. We get that, and every time we're debating if we should write another function or just add another parameter to an existing function, we're doing all that, and good stuff has been written about it. I'm familiar with some of the writings of Jim Coupline. What I would like to do today is take some of the thinking from the world of software design and bring it into the world of domain-driven design, or domain analysis, or domain modeling. And I'd like to talk about 4 things today, 3 things and an example, to be more specific. I want to talk about abstraction. Why is abstraction? What is an abstraction? What is abstraction and why it's important? I'll talk about how we build a theory. And I'll talk about CVA. CVA is short for Commonality Variability Analysis. And then I hope we will have time to present an example. So let's talk a bit about abstraction. Abstraction has been mentioned here a lot. We all have a good intuition of what abstraction is, so I'm going to be stating quite the obvious. Abstraction is the removal of characteristics from something to reduce it to its essential characteristics. And this statement believes, or is written under the assumption that things can be described in terms of their characteristics. When we say characteristics, we typically mean relationships and behaviors. And we also imply that some of those characteristics, those relationships and behaviors, some of them are essential, or at least essential in a certain context. And that when I remove the characteristics until I'm left with the essential characteristics, I might say that I have abstracted something. This is an abstraction of a smiling face. It's not a smiling face. It's an abstraction of a smiling face. It's an attempt to capture all those things that are common among all the smiling faces that we know. This is the Samsung smiley. And commonality is what allows abstraction. So in some sense, all smiles look like this. Anytime we've seen anybody smile at us, that's how they look. Now the truth is, in my experience, no smile looks like this. Each smile has its unique particularities, has its uniqueness, and variability is the essence of living, of being. When we say that one of the most beautiful things in the world, maybe the most beautiful thing in the world, is the smile of another human being, we don't mean that thing. We mean the smile of our parents, our grandparents, our children, our loved ones. That's what gives a smile its beauty. And it's the combination of the generic smile that they have and her own particular implementation of the generic smile that makes her smile so beautiful. And that's why we're so charmed when people smile at us. And this intuition really, in some sense, maybe it goes really deep into our humanity. And when we talk about our humanity as human beings, we say on the one hand, we all have our shared humanity. We all have common genetic roots. We all are equal in some sense, and that has some moral demands of us. We should offer each other equal opportunities. We shouldn't be bigoted or chauvinistic or racist or discriminatory against each other. Then we go on to say, each one of us is a unique composition of their genetic baggage, environmental baggage, cultural baggage, their passions, their wills, their likes, their interests, and never in the history of history has there been anybody like you, because you are extremely unique in your combination of the generic humanity and in your individual humanity, and that's what made you you. And that obligates you, we might say in some sense. You have to maximize your potentials, you have to maximize your abilities, you have to maximize your skills, your passions, and so forth, because there's nobody else in the world that can do it, because you're the only you that there is. So we have an understanding of our generic humanity or our abstract humanity that obligates us in some way, and we have an understanding of our individual, our personal humanity that obligates us in a different way. And when we talk about abstraction, we could start categorizing, we could start organizing things. Abstraction allows us to categorize because things are similar at some level. Once we can categorize them, we could start organizing them. Then we can make some order in the world. Now, mind you, at least in my home, and I imagine in many of your homes, in every home, in every office, in every inbox, there is something called odds and ends, the miscellaneous, the things that aren't easily abstracted. And sometimes we would find that this is the most useful drawer. So if I have the work-related and home-related and personal-related and all kinds of inboxes or in all kinds of folders in my email, then I have another folder called everything else or miscellaneous or odds and ends. And the reason that that exists is because not everything always fits neatly into a category. And not always is it worth the effort of abstracting. Sometimes it's nice putting the miscellaneous together. And maybe that's something to keep in mind when we do domain modeling is allow some room for the miscellaneous too. Even if you can't really abstract everything and categorize and organize everything, and you ask about something, is this a that or a this? Maybe it's neither. Maybe it's its own category, but it's not worth making a category up for it. It just is. And you could allow for miscellaneousness. So once we're able to abstract and categorize and organize, we could start talking about understanding the world. We can't understand the world unless our knowledge is organized. Synonyms for understanding might be things like grasp or comprehend. When we talk about understanding or comprehending, we're talking about taking the data and being able to derive, or the thing, the object of study, and being able to manipulate it and study it and come up with new insights that I wasn't told, come up with new insights that derive from my understanding of the generalities and the abstractions and the variabilities. And then I'm able to claim that I understand. And once I understand, then I'm able to go ahead and build a theory. So I want to talk about building a theory. This part of the talk is based on an article I read by Peter Naur. Peter Naur is a Danish, of blessed memory, is a Danish software scientist, computer scientist. He's the N in BNF, the Backus-Naur form. It talks about how you make formal languages. And he won the Turing Award, and about 30 years ago, he wrote a very interesting collection of essays called Computing a Human Activity. And in this wonderful collection of essays, there's a great essay called Programming as Theory Building. And this was brought to my attention by Professor West in an article of his called Why Programming is Hard and Software Development is Mostly Impossible. Thank you. It's really a delightful collection of articles, not easy to come by. This particular article is also in the appendix to the book by Alistair Coburn on Agile. So this particular article can be found. And there are many, many insights in this wonderful book and in this wonderful article. And one of his insights is that software is created by humans for humans. Oh, we've all been enlightened now. And when I was thinking about this, I was trying to think about how insightful is this? And I was reminded of the work by Tversky and Kahneman. Tversky and Kahneman, two Israeli economists who did a lot of work on modeling how people behave in the economics world. And they made the following statement. The value function for losses, say Tversky and Kahneman, the value function for losses is different than the one for gains. And those 12 words won them the Nobel Prize, at least Kahneman, who was still alive at the time. So that's insight. The value function for losses is different than the one for gains. And what does this mean? Until Kahneman and Tversky came around, the economists assumed that as long as everybody in the market is sophisticated, smart, well-informed, operating in his own interest, the markets will behave in a predictable, rational way. And people will value 10 euros as 10 euros, whether I'm about to gain or about to lose 10 euros. And Tversky and Kahneman came along and said, no, economists are not machines. They're not game theory machines. They're human beings. And human beings are more afraid of losing the 10 euros they have than they are greedy to earn the 10 euros they don't have. In their terms, they say we are loss averse. We don't like losing. We like winning. And we are risk averse. We don't take risks. And they were able to model that. And they were able to establish that it happens and it crosses cultures, it crosses environments. Now, the truth is, the only people that didn't know that were economists. Anybody that deals with with trading, merchants, advertisers, salesmen, peddlers, whoever. They all knew this all the time. They all knew that people are more afraid of losing money than they are eager to win money. And they were always able to use it to your advantage. Anybody that has said 30-day back guarantee or something, buy it, get it for free, and then later on are operating under the premise, well, I'll take it because it's for free. And then to give up something that I own already, that's a little harder for me. So they knew it and they were able to model it. So that was their insight. The insight is once there are human beings playing in the field of economics, things are different. So Peter Naur, the guy that did a lot of the groundwork when discussing formal languages, is the one that says, if you want to understand how software works, how software development works, you have to understand how people communicate to each other. The primary audience, besides the very, very trivial programs, the primary audience of your software is other programmers. The compiler could read machine code. The compiler doesn't need clear, well-articulated software in order to run it. And the work of the software giants, people like Turing, Babbage, von Neumann, who discussed Knuth, who discussed the limits of computability and what can be done by a computer and how far will a computer go, they sometimes related to the person in the process as something in the way. So when Lady Lovelace talks about programmers and people that are trying to build software, she had a concept of software to some sense, it's the intellect that's holding me back. If it wasn't for that mind encapsulated in my brain, in my head, that was holding me back, I would be able to do amazing things. And it's just the humans in the way. And Naur says software is about humans. It's humans that are communicating. And even though Naur didn't talk specifically, as far as I know, about doing domain analysis and domain design, we could take some inspiration from his thinking and bring it into the world of DDD. And most of what we do in DDD is a human activity. When we talk about things like ubiquitous language, we don't mean Java, we mean spoken language. When we talk about conceptual contours, when we talk about context mappings, these are all things that allow people to communicate with each other. These are not things that allow us to communicate with machines. And it's something to be very, very much important to be aware of. We're talking to each other when we're doing domain-driven design. And that's, by the way, at least personally, what makes the conferences so much fun for me, because people are much more fun than machines. Machines are fun too, but really, people is where it's at. And he said, Peter Naur, that the program must be supported by a theory. In order to understand that statement, let's understand what is a theory. A theory is a collection of beliefs and statements and ideas that, when put together, give me a consistent picture of why things are the way they are. A good example for theory might come from the world of storytelling. When I listen to a story, or when I watch a movie, or when I'm observing something with plot in it, stories all take place in time, of course. What am I doing? What I'm doing is I'm taking my knowledge of the world, which I got from other stories, or I got from my friends, my parents, my culture, my environment, whatever it is. And I'm bringing in the behavior of the actors in the story, of the people. And I'm constantly building a theory of why are people doing what they're doing, and why are people behaving the way they're behaving. And I'm slowly building a theory. And if the story supports a consistent theory, then I might say that the story was memorable, the story was good in some sense, the story was an exciting story. And if the story can't support a cohesive theory that's disjointed and the things don't make sense, and I can't think why did people behave the way they did and there's no consistency in their actions, then I might say that the story was forgettable or boring. I'm building a theory. And that's why the first time I read a story is qualitatively different than any other times I read the story. We hate spoilers because don't rob me of my first time that I'm exposed to the story or the movie, because I want to build the theory myself. I want to take the knowledge from the outside world. I want to take the information that the author or creator or actor of the story is giving me, and I want to build a theory. And if you tell me what happened at the end, so you saved me time because now I don't have to read the story, but you robbed me of an experience. I want to read the story. I want to go through the emotional, intellectual exercise of building that theory. So that's theory building. And storytelling is very, very tightly bound to theory building. I'm building my world picture. And what Peter now says is that the program must be supported by a theory. We must have some, if it's going to be good, we must have some collection of statements and beliefs that unify together, he's talking about software development, to make software. And that theory, in his opinion, should be shared among all members of the team or of the people that are working on the software. That means they don't only have to know what the modules do and why they do what they do. You have to have a good worldview about why things are the way they are. And when you bring in a new software developer into your team, you have to tell her, this is what we believe, this is why it is, this is how we imagine the software evolving over time. And what he claims is, when he talks about refactoring, he says, when you change software, be aware. Are you changing the text of the software, or are you changing the theory of the software? And if you're not aware of the two, you're going to cause software decline, software erosion. Software gets eroded when people make changes to the software and they're not clear to themselves. Am I changing something structural, theoretical, or am I just changing some words? And it's also important to us when we do domain modeling. When I'm doing domain modeling and I decide the sticky doesn't go here, it goes there. Am I moving it for topographical considerations, or for convenience considerations, or for spelling, or for clarity? Or am I doing it because I want to change the model? And if you're aware of that, you will be able to make good models. And if you're not good at that, no. And as a speaker, when I'm rehearsing my talk and I'm trying to think of different ways to perhaps express or articulate myself, or to say certain ideas, or how do I communicate my thoughts to the audience, I have to be highly aware as a speaker in preparation. Am I changing just the words and saying the same thing, the same idea in different words? Or am I actually changing the structure of my talk? Am I saying something else? And what allows for a good, compelling talk is, as part of your preparation, whenever you give talks, be aware, am I refining the idea, or am I just refining the words? They're both important. They both have to be done. But you have to, in order to have a good talk, you should be aware of what you're doing. And what Peter Naur says is, the dependence of a theory on a grasp of certain kinds of similarity between situations and events of the real world gives the reason why. The knowledge held by someone who has the theory could not, in principle, be expressed in terms of rules. This is a strong statement. He's saying basically, you cannot make the implicit explicit. You cannot express everything in terms of rules. There's some real-world knowledge out there that has come to you in terms of theory, that you know it, you understand it, and the rules won't capture all of it. And the theory is not equal to model. And when we say things like, understanding is more important than documentation, we're saying theory is more important than model. Understanding what you're doing and being able to make the statements and beliefs and have them work in a consistent way, that is more important to us than the model. Now, what do we do when we do domain-driven design? Well, we study the domain, and when we study the domain, we have, hopefully in the room, a domain expert, and hopefully that domain expert indeed knows something about the domain, and he's not just called that. And one of the things that the domain expert might be able to do is tell us concrete stories, real stories, not rules. And then we try to understand the domain. We build a theory. We might call this the discovery phase. And when we do event modeling, the primary objective of event modeling is not the outcome, the artifact. It's the theory that emerges while we are doing the event modeling. It's a person that has come out of an event modeling session is a transformed person, or woman or man. They're different. They now understand something deep that they didn't understand before they went into the event storming session. And it's highly, highly iterative. That means I hear a story, I modify my theory, maybe I even modify the model. I go back, I hear some more story, modify the theory, and then I go and I slowly modify my model. And that event storming, what it's part of the discovery phase, it's part of the analysis phase, it's part of trying to understand the domain and build a theory. That's what we are doing. We're trying to find abstractions. Now, we might point to the domain expert and say, tell me the rule. Maybe the domain expert knows the rule, maybe he doesn't. Maybe he's imagining he knows the rule, but he doesn't. We've seen it very often, all of us, that the domain expert says, oh, I know the rule, and he tells you a rule. And then you ask him about an exception, and he'll say, oh, well, maybe I have to restate the rule or rethink the rule, but that's how it is. And you slowly, with that engagement, you are building a theory, and that's an important part of what we do. So, when we do domain modeling, we first have to gather information. We might call that knowing, the raw knowledge. The difference between knowing and understanding is intuitive to all of us. We understand, we start mining rules and generalizations. We start taking those rules and generalizations and building them into a theory. And then maybe at some point we'll have a model. There'll be a specific set of rules that can be represented in some way that will give us an actual model that we could show, that we could talk about. I'll bring an example to talk about the difference between model and theory. I'll bring a few examples. They're important ones. Newton had a theory. The theory was, Isaac Newton that is, the rules that govern pendulums and planetary motion are the same. They can be discovered and expressed in mathematical terms. That was a theory. That's not a rule. It's a theory. He said there's some explanations and beliefs out there that could explain the world, and I'm going to try to discover them and articulate them as rules. And he found a model, and it's a useful model. And we know about models. I'll actually get to that a bit later. Theories can be true. Models are almost never true. And the difference between a theory and a model is, a theory is a set of abstract statements and beliefs that can explain a phenomenon. Phenomenon, I'm using it in the widest sense of the term. A model is a purposeful representation of reality. Now we have the representation of the model and the mental model, and there's some gap between them, but a model is essentially a representation of reality. And a correct theory will help us create useful models, and will help us use those models in an effective way. And if I don't have a good theory, it's very hard for me to create useful models. I want to bring an example. George Box. George Box was a British statistician. He studied data sciences, and he was very interested, this George Box guy, in how epidemics spread, or how ideas spread, or how fashion spread, how culture spread. He even asked questions like, how does a standing ovation happen? Where does it emerge from? And what's the critical mass for a standing ovation? And what George Box did was he created models to model these things. And when people started putting too much hope or too much faith in the models, then George Box said, all models are wrong. Some are usable. And this has been copied over or been quoted by Jerry Weinberg, I think, in the context of software modeling. But as far as I was able to discover, George Box is the originator of this statement. Now, I'm going to be a bit recursive here. Allow me. I think that the model, all models are wrong, some are useful, I think it's wrong. I think it's wrong, but it's useful. And I'll explain why it's a wrong statement, and I'll explain why it's a useful statement. And it's useful because it supports a theory. Now, it's wrong because in the George Box world, I have two groups of models. I have the right models, and I have the wrong models. And the right models, there's nothing there. And all the models in the world have been grouped into the wrong models. And the interesting wrong models are the wrong but useful models. And that is a wrong way to look at models. Models are not binary right or wrong. They can be a little right and a little wrong. They could be fit for purpose. They could be useful in some contexts. And of course, the utility of a model is highly dependent on it being correct. A totally wrong model can't be useful. But the theory behind what George Box is saying is, the theory is the models have to support a theory. The models have to support something. They have to be useful in some sense. The main objective of a model in George Box's world, and I agree with him, is its utility. Don't lose sight of that. The main objective of the model is its utility. Of course, a model has to be right in order for it to be useful. So that's the example of the difference between model and theory. We'll have some more examples later. So back to DDD. What we're doing in DDD, once again, is building a theory. We're trying to get a collection of statements and beliefs about the world that will hopefully be supported by a model. Okay. By the way, one note I want to make about Wardley maps. The domain, our theory of the domain, is not only what the domain is, it's what the domain will be, and what the domain will be once our model comes into it. Like Kahneman and Tversky asked themselves, when they were talking about people being risk-averse, they asked, how will people behave differently once they know about it, once they know that they're risk-averse? And the answer is, they behave the same. But at least they could write software that protects them from themselves. At least they could do other things. But it's an interesting question to ask. And our theory of domain is, what is the domain and how will the domain be different once our software interacts with it? Okay, so we spoke about abstraction, we spoke about models. I want to talk about commonality variability analysis. CVA is about the discussion or the analysis of how are things the same or how are they different in a significant way, because everything can be same or different in some non-significant way, and of course, it's highly, highly contextual. And the truth is that a lot of the geniuses, a lot of the breakthroughs in computer science were really breakthroughs in commonality variability analysis. The great Arab mathematician, Al-Khwarizmi, what he was able to do when he invented the algorithm. And the algorithm, which is to us, we all know what algorithms are. We use them all the time. His insight was you can take some parts of the mathematical statement and bind them or concretize them, and that is the algorithm. And you take the other parts and you parameterize them. And putting them together, you're able to predict how mathematical models will behave in the future. And one of the things that high school students struggle with so much is the difference between a parameter and a variable. If you don't have that deep parameters and variables, they could both change, but they just change at a different way. The Gang of Four, they said there's enough commonality among the way we do things that we could write patterns, and the patterns capture all those commonality. Now, you didn't finish when you learned about the patterns. You still have to apply the patterns to the particular domain at hand, and that is done by some instance of it. And you could go on and on. The generic, or what we call the universal Turing engine. The universal Turing engine is a great exercise in commonality variability analysis, or the common reference architecture by von Neumann. And when we say that somebody is intelligent, it means that they know when differences and similarities matter. And when we say that somebody is a genius, they noticed differences and similarities that nobody noticed. And when we say he's a fool, we say he didn't realize that the differences matter. One of the most foolish statements we all know is, that's the same, isn't it? And yes, at some level it is the same, but the importance, the significance is not in the sameness. The significance is in the difference. And when we talk about commonality, we might use words like learning, induction, deduction, experience, automation, production. And when we talk about boring, what we're saying is, I've seen it before, I've done it before. Those are all commonalities. And when we talk about variability, we're talking about words like novelty, intuition, discovery, exception, uniqueness, prototyping, and perhaps interesting. And it's the combination of two that brings us into what makes our world so exciting and makes life worth living. So when we talk about similarities and differences, we have to talk, of course, between classes. Classes can be the same and different, maybe types. We could talk about objects of the same class or of different classes. We could talk about change over time, change over space. These are all important things to know, and we have to talk about positive and negative variability. I want to talk a few minutes about positive and negative variability and why it is so important. So let's take an example of the positive and negative variance. And this is unique to domain-driven design. It doesn't map well into software. So let's say I'm talking about a message, any kind of message. Every message has a source destination. Every message has a body. That's a useful description of a message. It might even be true. And a positive variant of that would be a message with an expiry date. That is a positive variant. That means every true statement about message is true about my heartbeat. Heartbeat also has a source and a destination. A destination could be one or many. And it has a body. A negative variant would be a message without a body. Now, those of us that are in the software world, especially in strong type languages like C++ would say, but if you allow for a message without a body, then you weren't telling the truth when you said every message has a body. And C++ does not easily model negative variance. Yeah, you could do it with private inheritance or something like that. You can model negative variance, but it doesn't come intuitively to object-oriented developers. It comes very intuitively to real-world people. They say you could say a rule like everything behaves one way, and yeah, there are exceptions. There are exceptions to it. And so the programmer might say, well, let's take away every message has a body. And the positive variant will be, there's a message with an expiry date and a message with a body, and I don't need a negative variant. A NAC is a message like any other message. It doesn't have a body. The problem with that is I just lost the rule. I had a great rule. I had a useful rule that said every message has a body. Rules with exceptions are good rules. They're useful rules. I want to stick with this one. Rules with exceptions are useful rules, and I want to bring about my principle of useful generalizations. This is Avraham's principle of useful generalizations, and I like it. And here what it says. The words never and always are rarely true, but are often useful. Now, I'll let you see my first draft of this belief of mine. My first draft was, the words never and always are never true, but are always useful. Now, I didn't use this first draft because it's not true or useful. It's only funny. But so I decided to stick with the words never and always are rarely true, but they are often useful. And as domain modelers, we shouldn't be afraid of using them. As software developers, always only has one meaning when you're writing software, so be careful. But we're not software developers, at least not at this conference. At this conference, we're domain modelers and allow the words always and never. I want to bring an example. Now, this example is going to teach us the difference between class and type and instance and attribute, and it's going to teach us the importance of exceptions. So, I want to tell you a bit about birds. All birds have feathers, and all birds fly. Now, there might be some exceptions to that. For instance, I might tell you about the penguin or the ostrich. They have feathers, but they don't fly. Now, of course, I can tell you about the turkey. The turkey doesn't have feathers and doesn't fly, at least the cooked turkey, that is, right? This turkey here doesn't have feathers, and it's probably not going to fly. And the truth is, lots of birds don't fly. Birds that are feeding their young right now don't fly. Birds that are nesting on an egg don't fly. Birds that just don't feel like flying don't fly. Birds that are injured might not fly right now. Toy birds don't fly. Cartoon birds don't fly. And hearing this, you're saying to yourself, that's a stupid example. You're mixing up types of birds and states of birds and instances of birds and particular preferences of individual birds. The bird in the cage doesn't fly and the ostrich doesn't fly, but they don't not fly in different ways. There's different not flightness about this. And when we do domain modeling, we have to be careful. When I say it doesn't, am I meaning it never does? Is it a type of doesn't? Or is it a state of doesn't? And that's a real important question to ask when you're talking to your domain expert. This can't do that. Never, by virtue of its type, or it can't do it in its current state, or it can't do it if it decides not to do it. A real interesting one, of course, is a toy bird. Toy bird, of course toy birds don't fly. They're just models of birds. Models never do what the real thing does. Models do, they represent models, right? So like Eric Evans said in a lecture a couple years ago, the map is not the real world, it models the real world. So the fact that the toy bird doesn't fly or the cartoon bird doesn't fly doesn't upset me in any way. It shouldn't, because it's a model of a bird. And when Emily Dickinson, the great American poet, says, hope is the thing with feathers that perches in the soul and sings the tune without the words and never stops at all. There's an assumption here that things with feathers fly. And if you don't have that immediate image, then this poem doesn't do it for you. If you've been modeling, if you're a taxonomist or you're a software modeler of some kind, and you say, well, some birds have feathers, some don't, and some fly and some don't, and feathers and flight don't immediately bind into your mind into this association that also reminds us of hope and perching on the window, the perches in the soul, sorry, you won't get this poem. And That's your loss. So let's talk briefly about binding time. Binding time is when a parameter or a variable gets its concrete value. So as soon as I took this structure, I knew that I'm talking about a canonical shape. As soon as I gave the exponent of 2 and I gave it a, b, and c, I decided that not only am I talking about some sort of polygonal shape, I'm talking about an oval. As soon as I gave a, b, and c values, I decided that I'm talking about a particular oval. And as soon as I gave x and y values, I decided that I'm talking about a particular point on a particular oval. And that's what binding time is. And part of what we do when we do domain analysis is when we have variables and different things could have different values, we ask ourselves, when does it get its value? It could be, so when we're talking about software, it could be at design time. Some things get their value, get their binding in design time. Some get their binding at coding time or at compile time, deployment time, configuration time, runtime. Some functions only get their binding when I enter the function or when I enter the particular scope. And we get that. We've all written enough software, at least those of us that have, to understand this. We're talking about binding time in domain-driven design. It's a lot harder. It's a lot harder because each domain is different. The domain on the left column is the domain of software development. All software is the same in the sense, forgive the foolishness of the statement, but all software is the same in the sense that you write it, compile it, deliver it, and hope that it works, and then fix it when it breaks. But that means, so at some level, all software is the same. It's comprised of modules and functions and what have you. Domains are all different. Domains are different. So I might decide some things at design time, deployment, configuration. Some things happen at upgrade time. But some things might happen at account creation. Why? Because that's a domain-specific thing, and there are certain variables that happen at account creation and can't change, and so forth. So now, we spoke about abstraction, we spoke about theory building, CVA, and we have a few minutes left for an example, and we might even be able to finish a few moments early. So, I want to talk about a loan. This is a bank that sometimes gives loans, sometimes it doesn't give loans. So somebody that needs money comes to the bank and he asks the bank for a particular loan, and the bank might either grant or deny him a loan at the particular interest. And we are requested, and this is a human-machine kind of environment where some rules are made up by the machine or whoever programmed the machine, some rules are enforced by the human being, let's call her a loan officer, we're doing some domain analysis. Maybe we have to create some software in order to support this. So we opened the book by Martin Fowler, and the book has things called accounting patterns. And accounting patterns say all accounts, forgive the word all, many accounts follow this structure. And now, of course, Martin Fowler isn't naive enough to think that we finish there. Okay, we take the pattern, and then we take our particulars of our particular domain, and we try to apply the pattern if the pattern is appropriate. And I start doing some discovery, some domain analysis on this loan bank. And I start asking for stories. Tell me the story about a person that came to ask for a loan. And they tell me a story. They say, a 35-year-old, bankrupt, single mother, came in by bus and asked for $300,000 loan at 0.5% interest, and the bank manager said no. Okay, that's a story. The next story is whatever, and we go through the stories, and I'm starting to get rules, and I start generalizing, and I hear things like the occupation, the gender, the loan purpose. The officer always asks for the loan purpose. Is this for investment or for studying, finishing a PhD, going on vacation, paying off a different kind of debt? Are you being held for ransom or blackmail, and you need the money? Okay, people might need a loan for that kind of thing too. How much was the loan? Was the loan granted or not? Was the interest that he requested indeed the interest that he got? And over the lifetime of the loan, was this loan ever paid or not? And what did you do when it wasn't paid? And I start learning about types of loan. There's the studies loan and the investment loan, and there's the business loan. And the business loan has like we want to start a new business. I have ongoing expenses. There's a corporate loan. Why does he need a corporate loan? Is he trying to expand himself, or to just prevent himself from allow himself to avoid bankruptcy? And there are attributes of loan. So the borrower, I noticed that the borrower, from the moment the loan is taken until the moment the loan is paid, the borrower never changes. Well, maybe if he dies in the middle, or if he's a corporation, but for the most part, at least on personal loans, the borrower is the borrower through and through. That's a thing worth noting. You can't sell or buy a loan. Most people won't do that. Maybe they will. The interest. The interest is set at the loan time, but it might be variable interest, and then it'll change every period. It might be fixed interest and will still change to a variable interest loan. You could do that. Or it might be a variable interest loan and it'll change to a fixed interest loan. So loan interest does change, and the change changes. How much loan is outstanding? That changes all the time. Every payment, that changes. Every interest cadence, that changes. It's changing all the time. Who is the approving loan officer? She writes her name on the bottom of the form, and that sticks forever. You can't change it. And if she says, oh, I wished I never approved that loan, would you mind becoming the approving officer on my loan that I granted? Probably she won't be able to. Her name is associated with that loan until the loan is paid, and maybe even afterward. Was there some collateral for that loan? A home, a business? What is the maximum loan allowed? This isn't really an attribute of the loan. It might be an attribute of the borrower. It might be an attribute of the borrower type. That means a homeowner could only borrow up to 100,000 euro. This homeowner could only borrow up to 10 euro because he has some bad behavior in his past. What is the type of the bank that could grant the loan? Some banks are allowed big loans. Some banks could only give small loans. And what's the maximum type that a loan officer could approve? Maybe she could only approve up to 100,000 euros, and if you want to approve 1 million euros or 100 million euros, we have to call in the next level, show me your manager or something like that. And I notice states of loan. There's before and during and after. And before, a loan might be in the application process, it might be reviewed, might be denied, and then it never gets any further, but it's interesting to know about. A loan might be approved. A loan might have some sort of conditional approval or conditional denial. And again, the purists might say, isn't conditional approval and conditional denial the same? No. If I go to a borrower and say, yes, the loan is approved, all you have to do is sign this paper. That's a very different story than saying, I'm sorry, ma'am, the loan isn't approved. Unless you could sign this particular paper, then I'll be able to approve the loan. They might end up actually being implemented the same in software. But when doing the domain modeling and trying to see, I might say there's some important differences between the conditional approval and the conditional denial that actually matter in implementation. And matter, for instance, who has discretion to waive the requirement might change if it's conditional approval or conditional denial. If it's conditionally denied, maybe you won't get the loan unless you bring a particular document. Nobody could waive that requirement. And then when we tell somebody, you will get the loan as long as you bring a particular document, and then the bank manager sticks his head out of his office and says, hey, he's my brother-in-law, it's okay, you could waive that one. Maybe that's allowed, I don't know. And then we had this weird loan called the charity loan. These are these low interest, you never expect to get them back kind of loan. The bank doesn't like giving them, they probably never give them. They're these kind of pro bono loans to the extent that maybe they're not even worth modeling. Maybe they bring more noise into the system than anything else, and they have their own special way of handling them, and it's actually not so good to model them because if a regulator catches them, then he's going to start asking uncomfortable questions. So I might even decide that it's against my interest to model the charity loan. And I have types of banks. I have the small, medium, and large. And I noticed that when I install the software, I really can't change it. So if I installed the small bank version of the software, even if the bank grew, I probably have to uninstall the software, get new servers, get new systems, and install new kinds of software. So for instance, there's probably no point in me making a installation time parameter. Are you a small bank, a medium-sized bank, or a corporate bank with 300 branches? Because it's going to be different software, different servers. We don't need one kind of software that supports all of them. And I start asking the questions, and I start building myself a theory. And the theory is that risk is at play here. Now, we've all taken loans, and we've all read the basic books on economics. We all know that loans and interest is about risk. So I don't need a domain expert to come along and say, loans are about risk. I knew that already. But what the domain expert might tell me, or what my theory building might tell me is, there are all kinds of nuances here about risk that have never been properly expressed. And I might start asking questions like, risk of what? Is it risk of losing money? Risk of losing all your money? Risk of going to jail? Risk of the bank going bankrupt? Who is the risk to? Is the risk to the bank? Is the risk to the loan officer? Is the risk to the bank manager? And I noticed that there's actually one risk that nobody really cares about, and that's the risk to the borrower. Maybe the borrower is going to die of a heart attack in 4 years because he won't be able to pay this loan and the bank is going to hound him down. Okay, well, that's his problem. He shouldn't take loans that he can't sleep at night with. And I also noticed that the risk of losing money might be larger or greater than the risk of missing an opportunity. So there's a risk that maybe I could have given this loan and it would have actually been paid back, and now I lost an opportunity to give a loan. Maybe nobody cares about that, or they don't care about it as much. They're more concerned about the risk of losing money. And when I'm building the software that's going to support the loan officer in deciding to grant the risk and how much interest to allow and how to mitigate that risk, I might need to start gaining an intuition of these things. And of course, there are other risks that might not be modeled at all, right? That means if somebody comes in and she asks for a loan to finish her studies, and you're running a risk that there's a PhD student that could have finished her thesis, and she didn't because she didn't get the student loan. And you could have helped her, and you lost that opportunity to help somebody finish their studies. The loan officer might say, as a parent, I would certainly care about that, but as a loan officer, that's not a risk, that's not a missed opportunity that I even know how to think about, and I know how to model, and I know how to put in software. Maybe it shouldn't be that way, but as software modelers, we don't always talk about how things should be. We just discuss the way they are. So I create this model, and the model is that certain things feed into the risk, and the risk feeds other things, and that the naive model that we all learned is risk equals likelihood times loss, and there are feedback loops. I reduce the risk. This is not really true. The risk is really, really complicated, how to calculate risk, and risk is something that's ongoing and needs to be maintained, and we have to model our risk. And if I start creating my object model, maybe I'll say that I have my loan, and there are 3 types of loan. There's the private, business, and corporate. And I might decide, well, corporate is so different, I'm not even going to talk about it today. There are certain things that the corporate loan has in common with the private and business loan. No denying. It's also about risk management. It's also about interest. It also needs to be paid back. But it's so different that at least today, I'm going to start on modeling the private and business loan. And the private loan might be a student loan or a mortgage loan, might be a short-term loan or a long-term loan. And the business might be to expand my business or to pay off a debt. And then I noticed that at least for today, perhaps the short-term loan and long-term mortgage, they're the same, or they're enough the same that that they don't change the risk in an essential way. And since I developed a theory, and the theory told me that it's all about risk, I'm probably going to want to focus my energy and my cognitive abilities and my brain power in properly modeling the risk. And that's where I'm going to take the domain expert and ask him, tell me about risk. Tell me about creating risk, avoiding risk. How do I model this? Are there rules that can be expressed? Let's explore the rules and see if they really support the theory. How much of the risk management do I give to the individual, and how much do I automate risk management? Do I allow the loan officer to take her personal impression into account, or not? Things like that. And how do I allow people to decide? So that's a very, very quick example. So we spoke about abstraction, about theory building. We talked a bit about CVA, and I brought a brief example about how we could do some of this, perhaps. And in summary, you should listen to individual stories, because the individual stories allow you to create generalizations. And stories are not user stories. Stories are stories with real people that went and did something, and you might catch on details that were not expressed in the user story. And notice when things are common, different, the same, and notice binding time. When did they become the same? When did they get their value? That's an important thing. And if exceptions can be ignored, ignore them. Don't get caught up on the exceptions. When you write software, maybe you always have to write exception handling. Rebecca taught us some nice heuristics about handling exceptions or not. But when trying to model the real world, the exceptions can be extremely, extremely distracting. Create your theory. Allow yourself to have a theory, and don't attempt to make everything explicit. Not everything can be made explicit. And ensure that your model is supported by the theory. So as you're modifying the model, saying, am I changing my theory? And if I am, be explicit about that you should be explicit about. And saying, I'm changing the model because I'm actually changing my understanding. And that's it. And of course, you should smile. A smile is really, really the most beautiful thing you're ever going to see in the world, is another human being smile. Thank you for your time. Thank you for your attention.